In this lesson, we will take a closer look at the hydrogenic wave functions, which are more commonly referred to as atomic orbitals. As we have learned earlier, the electronic wave functions for a hydrogenic system can be written as a function that depends only on lowercase r, times a function that depends on theta and phi. The functions that depend on theta and phi are the spherical harmonics, and we've already examined these functions in detail in our lesson on the particle on a sphere. So now, we'll examine the radial function, which is typically represented by uppercase r and generally follows the form shown here. It depends only on lowercase r, the distance of the electron from the nucleus. Two quantum numbers, n and l, appear in the expression for the radial function as shown here in red. Uppercase N is the normalization constant. Z is the atomic number, and A0 is a collection of constants that evaluate to 52.9 picometers to 3 significant digits. A0 is referred to as the Bohr radius. So what information can be derived from the radial functions? Recall that the probability density function is just the square of the absolute value of psi. This means if we imagine moving away from the nucleus on a straight line in one specific direction, the variation in the probability of finding the electron is directly proportional to the square of the radial function. Note that for a given direction, theta and phi are constant, and so is the spherical harmonic. Of course, the probability does not vary if the spherical harmonic itself is zero. Let's see the general pattern in how the probability of finding the electron varies with distance by examining the factors in the expression for the radial function. The exponential factor makes the radial function go to zero as the distance approaches infinity. In other words, the probability of finding the electron eventually goes to zero as we move away from the nucleus. Furthermore, this exponential factor decays much faster with a larger z. This makes sense because if more protons are pulling the electron in, the less likely you will find it at larger distances away from the nucleus, all other parameters being the same. Let's dig deeper. In the general expression for the radial function shown here, the factor written as L of r is a polynomial function of r. These polynomial functions are called associated Laguerre polynomials, and they depend on quantum numbers n and l. The degree of these polynomials turns out to be n minus l minus 1. Recall that we refer to locations where the wave function goes to zero as it switches algebraic sign as nodes. Locations corresponding to roots of the associated Laguerre polynomial of a radial function are therefore referred to as radial nodes. This means that the wave function has n minus l minus 1 radial nodes, with a probability of finding the electron is zero. Since in 3 dimensions, all points equidistant from a given location constitute a spherical surface, a radial node is also referred to as a spherical node. A radial node is a spherical surface where the wave function and the probability of finding the electron goes to zero as it switches algebraic sign from inside the surface to outside. Let's take a look at an example. For a 3s orbital, the associated Laguerre polynomial in the radial function is given by 6 minus 6 rho plus rho squared. In this expression, rho is 2 times z times r divided by 3 times a0. How many radial nodes are there? Recall that for a 3s orbital, quantum number n is equal to 3, and quantum number l is equal to 0. Therefore, the number of nodes, n minus l minus 1, is 2. We expect 2 radial nodes. We can see that the degree of the polynomial is 2. A second-degree polynomial has 2 roots. Where are the 2 nodes located? We just have to find the rho values where the polynomial is equal to 0. In this case, we can use the quadratic formula since we have a second-degree polynomial. Once we find the values of rho, we can solve for the values of r for the 2 spherical nodes. Let's take a look at the r raised to the power l factor in the expression for the radial function. Since quantum number l is 0 for s orbitals, this factor is equal to 1 for s orbitals, regardless of r. The associated Laguerre polynomial L of r is non-zero at the nucleus, where r is 0. This means that the radial function is not 0 at the nucleus for s orbitals, but it is 0 for other types of orbitals. In other words, the probability of finding the electron at the nucleus is not 0 for s orbitals, but is 0 for other orbital types. Shown below are plots of the radial function for 1s, 2s, and 2p orbitals of hydrogen. One unit on the horizontal axis corresponds to 1 Bohr radius. Which plot corresponds to which orbital? Let's see. Recall that at the nucleus, the radial function is non-zero for s orbitals, but is 0 for others. This means that the two plots on the right are s orbitals. Note that the most probable location of the electron is at the nucleus. This is generally true for s orbitals. The one on the left, where the radial function is 0 at the nucleus, must be the plot for the 2p orbital. The number of radial nodes is n minus L minus 1. For the 1s orbital, n is 1 and L is 0. The number of radial nodes is 0. This corresponds to the plot in the middle. For the 2s orbital, n is 2 and L is 0. The number of radial nodes is 1. This corresponds to the plot on the right, which has 1 radial node. Note that for the 2p orbital, shown on the left, the radial function is 0 at the nucleus, and there is no radial node. For a 2p orbital, n is 2, L is 1, and n minus L minus 1 is 0. Note that the location of a nucleus, where r is equal to 0, is not considered a radial node, even though the radial function is 0 there. To visualize the probability of finding the electron around nucleus, we can examine cloud representations of the wave function, like the one shown here. In these representations, the cloud is thicker in regions where the square of the absolute value of psi is larger. In other words, the cloud is thicker in regions where the electron is more likely to be found. Often, in these representations, the cloud is color-coded to indicate the algebraic sign of the wave function. This facilitates visualization of the nodes. The example shown here is for a 2s orbital and was generated from Professor Winter's Orbitron website. The cloud is color-coded blue and white on a black background. The figure on top tries to convey the information in 3 dimensions. The bottom figure is a 2-dimensional cross-section of the top figure. Recall that a 2s orbital has 1 radial node. This radial node is a spherical surface separating the blue and white dots. In the 2-dimensional cross-section, the radial node is a circle. Note that the cloud is thickest at the nucleus. The most probable location of the electron in an s orbital is at the nucleus. Tracing a straight line starting from the nucleus, we can see the cloud thins out as we approach the node, thickens again as we move farther out, then thins out again at even larger distances. We can also see that the cloud is spherically symmetrical. This is because for s orbitals, the spherical harmonic does not depend on direction. Here's a 2-dimensional cloud representation for the 3pz orbital. The cloud is color-coded yellow and white to indicate regions of opposite algebraic signs for the wave function. The cloud is thicker at locations where the absolute value of psi squared is larger. We expect to see 1 radial node, since n minus L minus 1 is equal to 1. For a 3pz orbital, the quantum numbers n, L, and m are 3, 1, and 0, respectively. Here's the radial node. It's a spherical surface, and we can see that the cloud is white and yellow on opposite sides of the sphere. For any given direction, we can see that the cloud gets thicker as we move away from the nucleus, then thins out as we move farther out and approach the nodal sphere, thickens again as we continue moving away from the node, then eventually thins out as it approaches infinity. Regardless of direction, except at the xy plane, the cloud is thickest at the same distance from the nucleus. The xy plane in a 3pz orbital is an example of an angular node. Angular nodes are due to the spherical harmonic changing algebraic sign at a given value of theta or phi. For a pz orbital with quantum numbers L and m equal to 1 and 0, a node occurs at theta equals pi over 2. If you examine the figure shown here for a 3pz orbital, you can see that the cloud is thickest in the positive and negative z-axis directions. For a given distance, the cloud thins out as we head towards the xy plane, where theta is equal to pi over 2. This directionality, or dependence on direction, of the probability density is due to the dependence of the spherical harmonic on theta and phi, and is observed for non-s orbitals. Here's a comparison of the cloud representations, all drawn to the same scale of the atomic orbitals for n equals 1 to n equals 4. Only the orbitals with quantum number m equals 0 are shown. Let's compare the 1s, 2s, 3s, and 4s orbitals. It should be easy to see that the larger the quantum number n, we can expect the region where we are most likely to find the electron to be larger. Or we can say that the average distance of the electron from the nucleus increases as quantum number n increases. If you recall our lesson on the particle in a two-dimensional box, we can visualize the variation of the wave function on a plane by using contour plots. The figure here shows contour plots for the 3pz orbital on any plane that contains the z-axis. To interpret the plot, imagine each set of contours as a mountain with its peak at the center. All points on a contour line are at the same elevation. A higher elevation means a higher probability density. More closely spaced contours means a steeper mountain. Nodes are located at the valleys between the mountains, that is, at 0 elevation. Here's the radial node for the 3z orbital. Here's the angular node at the xy plane due to the spherical harmonic. It is often useful to use colors to indicate differences in the heights of the mountains. Contour lines with the same color in separate mountains represent the same elevation. Here, the peak heights of the two mountains closer to the xy plane are higher than the peaks of the ones farther away. An isosurface is a three-dimensional version of a contour line. All points on an isosurface have the same value of psi squared. For typical isosurface plots, the value of psi squared is chosen so that the surface encloses a region where the probability of finding the electron is high, like 90%, for example. Parts of the isosurface are also typically color-coded to indicate regions where the wave function has opposite algebraic signs. This facilitates visualization of the nodes. Here's an example of an isosurface for the 3pz orbital. Quantum number n equals 3, L equals 1, and m equals 0. This screenshot was obtained from the Orbitron website. The color coding makes it easy to identify the radial node here. The radial node is a spherical surface. Here it separates the two inner lobes from the outer lobes. For L equals 1 and m equals 0, the spherical harmonic has a node at theta equals pi over 2, which is the xy plane. The figure shown here is an isosurface plot for the 2s orbital. It is spherically symmetrical since the spherical harmonic does not depend on theta and phi. Note, however, that the 2s orbital does have one radial node, so another spherical surface with the same value of psi squared is inside the surface shown on the left. We need to imagine slicing this surface open to see the other surface. This is what it would look like. The radial node is the spherical surface between the blue sphere and the outer white sphere. The overall shapes of the orbitals are largely determined by the shape of the spherical harmonics. You need to be familiar with these shapes, as well as the effect of radial nodes. Here are the best interactive websites that you'll find most helpful. These are easily searchable, or you can scan the QR code shown here. Note that these websites only show real orbitals with no imaginary components. These would be orbitals for which the quantum number m is equal to 0, or linear combinations of pairs of orbitals with the same absolute value of quantum number m. For example, on these websites, you won't find isosurface plots for p plus 1 and p minus 1 orbitals. Instead, you'll find the real linear combinations px and py. The imaginary components in the orbital functions are due to the spherical harmonics. In a lesson on particle on a sphere, we discussed how we can replace these by equivalent functions with only real components. Recall that, among other things, one piece of information that we can obtain from the wave function describing a particle is the probability of finding it in a specified region of space. If we know the wave function for a stationary state, the probability of finding a particle that is bounded by x and x plus dx, y and y plus dy, z and z plus dz is given by the square of the absolute value of psi times dx, dy, dz. The product of dx, dy, and dz is often written as just dv. By now, you should know that the absolute value of psi squared is the probability density at a given location. In 3 dimensions, it's a probability per unit volume. It's easy to see that dv is the volume of a rectangular box with infinitesimally small length, width, and height of dx, dy, and dz, respectively. Thus, dv is called the volume element in the Cartesian coordinate system. If we're interested in a finite box, the probability is obtained by triple integration. If we integrate the square of the absolute value of psi with respect to x from x1 to x2, then integrate the result with respect to y from y1 to y2, then integrate the result with respect to z from z1 to z2, then we get the probability of finding the particle in a box bounded by x1 and x2, y1 and y2, and z1 and z2. The order of integration does not matter. In Cartesian coordinates, the volume element, dv, is dx times dy times dz. However, in spherical polar coordinates, dv is given by dr times r d theta times r sine theta d phi. So, the probability of finding a particle in a region bounded by r and r plus dr, theta and theta plus d theta, and phi plus d phi's, square the absolute value of psi squared times r squared times sine of theta times dr d theta d phi. When integrating for a region with boundaries defined by r1, r2, theta 1, theta 2, phi 1, and phi 2, we integrate with respect to phi from phi 1 to phi 2. Then we multiply the result by sine of theta before integrating with respect to theta from theta 1 to theta 2. Then we multiply the result by r squared before integrating with respect to r from r1 to r2. The order of integration does not matter. Here's a QR code linked to a reference regarding integration in spherical polar coordinates. Let's look at an example. How would you calculate the probability of finding the electron in a spherical shell with an inner radius of 5 picometers and an outer radius of 10 picometers below the xy plane and to the right of the xz plane? Here's the answer. We integrate the absolute value of psi squared with respect to phi from phi equal to 0 to phi equal to pi. These integration limits correspond to locations to the right of the xz plane. Then we multiply the result by sine theta and integrate with respect to theta from theta equal to pi over 2 to theta equal to pi. These integration limits correspond to locations below the xy plane. Then we multiply the result by r squared and integrate from 5 picometers to 10 picometers. What is the probability of finding the electron within a spherical shell of radius r and thickness dr? To answer this question, we have to integrate absolute value of psi squared, dv, but over all angles only. Here's the integral. Note that we integrate over all possible values of phi, that is from 0 to 2 pi. Then we multiply by sine theta and integrate over all possible values of theta, which is from 0 to pi. We can simplify this integral by replacing psi by the product of the radial function and the spherical harmonic. Since the radial function does not depend on theta and phi, as far as the integration with respect to these angles, the radial function is a constant, and we can pull it out of the integrals. We can also take out the radial function out of the absolute value symbol, since the radial function has no imaginary component. Since the spherical harmonics are normalized, this integral over all angles is equal to 1. And this expression simplifies to this: little r squared times big R squared times dr. This is the probability of finding the electron within a spherical shell of radius r and thickness dr. The function little r squared times big R squared is called the radial distribution function. Earlier, we learned that the square of the radial function, which is also known as the radial probability density function, tells us how the likelihood of finding the electron varies with distance from the nucleus along any one specific direction. That's because, for a given direction, the spherical harmonic is a constant, which makes the absolute value of psi squared directly proportional to the square of the radial function. So, along any specific direction, the most probable distance of the electron from the nucleus is where the maximum value of the radial probability density occurs. However, if we want to determine the most probable distance, taking into account all possible directions, we have to use the radial distribution function. For example, consider the 2s orbital of hydrogen. On the left, we have a plot of the radial probability density, big R squared versus distance in Bohr. On the right, we have a plot of the radial distribution function, little r squared times big R squared versus distance in Bohr. We can say from the radial probability density that we are most likely to find the electron at the nucleus, that is, at r equal to 0 for any given direction. However, from the radial distribution function, we can see that the most probable distance is around 5 Bohr. How could this be? We have to remember that all locations on a sphere that is centered on the nucleus are at the same distance from the nucleus. The larger the radius of the sphere, the larger the surface area of the sphere, the more locations there are for the electron to be at. The surface area of a sphere is directly proportional to the square of the radius, which in this case is little r. Therefore, the probability of finding the electron at distance little r, taking into account all possible directions, is proportional not just to big R squared, but also proportional to little r squared. We can use the radial distribution function to calculate the average distance of the electron from the nucleus. This is just the expectation value of little r. The expectation value of little r is calculated by multiplying it by the probability density function, then integrating over all space. It should be easy to show that this is equivalent to integrating the product of little r with the radial distribution function over all possible values of little r. If we work out the integral, we find the average distance to depend on quantum numbers n, L, and the atomic number Z. For hydrogen, here are some results. Let's summarize the trends. For the same Z, a larger quantum number n means that, on average, the electron is farther from the nucleus. For example, the average distance for the 1s orbital is 1.5 Bohr, while the average distances are larger for the 2s and 2p orbitals, which are 6 and 5 Bohrs, respectively. For the same Z and N, a larger quantum number L means that, on average, the electron is closer to the nucleus. For example, the average distance for the 3d orbital, with quantum number L equal to 2, is smaller compared to the 3p orbital, with L equal 1, which is smaller compared to the 3s orbital, with L equal to 0. How do you think Z affects the average distance? Intuitively, we expect a larger nuclear charge to pull in the electron more strongly. Based on the formula, to get the average values for helium ion, for example, we just divide the results for H by 2. In general, we can use the radial distribution function to calculate the average or expectation value of any function of little r. We just multiply the function by the radial distribution function and integrate over all possible values of little r. For example, the Coulombic potential energy is 1 over 4 pi epsilon naught times the nuclear charge, Z, times the charge of the electron, negative E, divided by the distance from the nucleus, little r. Evaluating the appropriate integral, we can find the expectation value of the potential energy to be 2 times the orbital energy E sub n. We can use the radial distribution function to determine the most probable distance of an electron from the nucleus. To do this, we plot the radial distribution function versus distance. The most probable distance is where the function reaches its maximum. For orbitals with quantum numbers n and l, plots of the radial distribution function exhibit n-l humps. The most probable distance is given by the peak of the outermost hump. Examine the figure below, which plots correspond to the radial distribution functions for 1s, 2s, and 2p orbitals. Let's see, of the three orbitals, only the 2s orbital has two humps. The quantum numbers n and l are 2 and 0. 2 minus 0 is 2. So, the red curve must be the radial distribution function for the 2s orbital. The peak of the outermost hump of the red curve corresponds to the most probable distance from the nucleus of an electron in the 2s orbital. The two other curves have only one hump, corresponding to the radial distribution functions for 1s and 2p. But which is which? Well, we expect the electron in a 1s orbital to be closer to the nucleus, on average. So the green curve corresponds to the radial distribution function for the 1s orbital. And the blue curve must correspond to the radial distribution function for the 2p orbital. We can calculate the most probable distance by setting the derivative of the radial distribution function with respect to distance r to 0. Then we solve for the r values where this condition is satisfied to find the local extrema. To test if a local extremum is a maximum, we can do the second derivative test, and maximum we expect of the plot to be concave downward and the second derivative to be negative. We can expect to find local maxima at n-l locations. The most probable location is the farthest of these locations, that is, the peak of the outermost hump.